MXT, the space of the all t invariant Borel probability measured on X. This space is a non-empty convex set and is compact with respect to X-star topology. EXT is a subset formed by ergodic measure, which exactly the extreme point of the space of the t invariant Borel probability measure. Let f be a continuous function on compact metric space X. We denote S and X is a sum from K0 till n-1 composition FTKX, and call this a Birkhoff sum. And we call limit 1 over n Birkhoff sum a Birkhoff average when n goes to infinity. By Birkhoff theorem, we know that the Birkhoff average exists for almost every point. We denote by alpha F the infimum of the Birkhoff average, and beta F the supremum of the Birkhoff average. Alpha F and beta F are called the minimal and maximal ergodic averages of F respectively. Since alpha F is equal to minus beta minus F, let us focus the discussion of the quantity beta. It can also be characterized as a beta F equal to supremum integral f du mu over the space of the t invariant Borel probability measure. Since the space of the t invariant Borel probability measure is a compact and convex, supremum attained, and such a measure we call it maximizing measure. And denote, this set with M max F. Assume that the entropy mass is an upper semi-continuous, so there exists an equilibrium measure mu t. We studied the behavior of the equilibrium measure mu t for a potential Tf when t goes to infinity. In the thermodynamic interpretation of the parameter T, it is the inverse temperature. The limit T goes to infinity are called zero temperature limits. The accumulation point of the measure mu T as a T goes to infinity are called grand states. Zero temperature limit laws are also related to ergodic optimization, because for T goes to infinity, any accumulation point mu of the equilibrium measure mu T will be a maximizing measure F. Moreover, we have the continuous of the zero temperature limit in the sense Lyapunov exponent entropy, more precisely limit integral f d mu t, t goes to infinity is equal integral f d mu, and the limit measure theoretical entropy mu t when t goes to infinity equal to entropy mu t. Since I'm working on compact metric space, these results are obvious. Moreover, these results are also true for non-compact setting. In fact, the first one, the continuity of the Lyapunov exponent was proven by Urbanski, Jenkinson, and modeling. And the second one was proven by Ian Morris for non-compact setting. As I mentioned, Birkhoff average exists for almost every point. So one may ask about the size of the set of the point where the Birkhoff average exists. We denote by EF alpha, where we call it alpha set of the Birkhoff spectral, where we're given alpha from the set L, set of the alpha such that there exists the X, and Birkhoff average is equal to alpha. We call Birkhoff spectral. The size usually calculated in terms of the topological entropy, in the sense of the bound, because the level set is not the compact set. We denote by P phi T the topological aperture for the potential T phi. It is well known when Xt is a transitive subshift finite term and the F is a continuous function, then level set is not empty set if and only if alpha belongs to omega. And topological entropy level set is equal infimo the topological aperture minus alpha T over T belong real numbers, and that's equal to supremum measure theoretical entropy such that mu belongs to a space T invariant probability measure with Lyapunov exponent is equal to alpha. This formula is called restricted variational principle because, as you see, we restricted to level set.
Reza, sorry, could I take you back a slide?
Yes.
So your two-way implication, the first display equation, was omega, big omega, was that defined somewhere before? I don't quite understand this. You're saying on the right you imply that omega is defined to be this set?
Yes, but what I'm just saying, this set is an alpha level set.
Yeah.
Yes.
Mm-hmm.
But what I'm just saying, by Birkhoff average, we know that's is equal to integral f d mu integral f d mu. So this is obvious. Whenever we have the alpha, there exists of the some T invariant probability measure integral f d mu. I'm just saying this one is a non-empty set.
Maybe I missed. Did you define big omega before? Or this is the definition?
No, I'm just defining here, as you see.
Okay. All right.
Omega, yeah. Omega is a set of the Lyapunov exponent measure.
Yeah. So Cecilia just commented something. Perhaps it's meant alpha in omega.
Yes, I mentioned.
Yeah, something like this. Yeah.
Yeah, I say alpha belongs to omega. Yeah, here I mean the alpha belongs to omega.
Oh, right. Okay.
Yeah,
that makes more sense.
Yeah, if you look here, say for all alpha belong of the omega.
Okay, thank you.
Yeah, you're welcome. Please stop me whenever you have any question or remarks. Assume that the phi n is a continuous positive value function on compact metric space X. We say that phi log phi n is the subadditive potential if phi n plus x is smaller or equal phi n x, phi m t n e and x for all x m n belong of the natural number. And almost additive potential if there exists the constant c greater or equal to 1 for all x m n belong of the natural number. We have a inverse of the c phi n x times phi m t n x, a smaller or equal phi n plus m, a smaller or equal c phi n x phi m t n. And we say that additive potential if phi n plus mx is equal to phi n x times phi m p n x for all x and mn. Birkhoff is an example of the additive potential. Let us see an example of subadditive potential. The natural example of subadditive potential is a matrix cocycle. More precisely, given a measurable map A from compact metric space X to invertible matrices, we consider the product A and X is equal A Tn minus mu till Ax. The pair Ta is called a linear cocycle. It induces a skew product dynamic F on X times Rd, where Xv goes to Tnx, Anxv. If T is invertible, then so is F. Moreover, you see the formula for inverse of the F. Let us see an example of the linear cocycle. A simple example of linear cocycle is a locally constant cocycle, which defined as a follows. X is a symbolic space, T is a shift map, given a finite set of the matrices, invertible matrices. We define a function A from X to invertible matrix take any point in X and we project to first coordinate. We project to first coordinate. That is why we call it locally constant cocycle. By Kieman's subadditive ergodic theorem, for any mu belong to a space of the two-invariant Borel probability measure, and mu always every X such that logarithm of the norm A is integrable, the following limit, called the topological exponent X, exists. X A is equal to limit 1 over n log norm A and X and goes to infinity. Let me mention existence of the topological exponent for matrix cocycle was proven in 1960 by Festenberg-Kirsten. Indeed, their result is a straightforward consequence of the Kieman subadditive theorem, where it was proven later, I believe in 1968. Where norm A is a Euclidean operator norm of the matrix A, largest singular value, that's the subadditive. Norm an plus m is equal, is a smaller equal to norm an x times an t m x for all xn. So as you see, linear cocycle is an example of the subadditive potential. Let us denote Lyapunov exponent measure by phi mu a. If the measure mu is ergodic, then top Lyapunov exponent is equal to Lyapunov exponent measure for mu almost every x. Similarly to what we did for Birkhoff averages, one can either minimize or maximize the top Lyapunov exponent. More precisely, we denote by alpha a the infimum of the top Lyapunov exponent, and that's equal to infimum of the Lyapunov exponent measure over the space of the T-invariant Borel probability measure. Also denote by beta a the supremum of the top Lyapunov exponent, that's equal to supremum of the Lyapunov exponent measure over the space of the T-invariant Borel probability measure. Since Lyapunov exponent measure is a subadditive, and the space of the T-invariant Borel probability measure is a compact and convex with respect to weak star topology, so supremum attained. Such a measure we call it Lyapunov maximizing measure. But this is not the necessary case for minimal Lyapunov exponents. That means there are examples that Lyapunov minimizing measure doesn't exist. In the case of locally constant cocycle, Bocchi-Morris proved that the minimal Lyapunov exponent is continuous under one domination assumption. Emmanuel Brouat and Charles Serret extended their result to joint spectral under domination assumption. Moreover, they gave a contour example that shows that we have a discontinuity of the minimal Lyapunov exponent for generic cocycles. I will explain what I mean generic cocycle. But in this context, locally constant cocycle, generic cocycle means pinching and strongly irreducible. Let us see another example of the linear cocycle. The linear cocycle generated by a diffeomorphism map T on a closed Riemannian manifold M to itself, a family map AX that's equal to derivative of the T that's from tangent space at the point X to tangent space at the point Tx are called derivative cocycles. Moreover, when T from X to itself is an honest diffeomorphism or expanding map, Bowen showed that there exists a symbolic coding of the T by subshift finite type. From now, I'm just working with a linear cocycle generated by following. T is a topological mixing subshift finite type. and A is a Holder continuous. I'm just working with this system, unless I mention something else. In general, we know that much more about a locally constant cocycle than about more general derivative cocycle. But here are some of the results known in the derivative cocycle situation. Our Holder continuous function A is called fiber branching if for any x nor ax times nor inverse ax times omega r is smaller 1, where omega is a hyperbolic constant defining the metric on the base sigma. We say that linear cocycle TA is a fiber brancher if its generator A is a fiber brancher. We denote by HBR, the family of the R-Holder continuous and fiber branching function. Since we are talking about the fiber branching assumption, let me mention something about the fiber branching. Fiber branching assumption is an open condition which roughly says that cocycles are nearly conformal. If you look at these things, you will understand what I mean by nearly conformal. Moreover, there was a conjecture due to Vienna that said Lyapunov exponent is continuous on two-dimensional fiber branching, the conjecture was proven by Aaron Brown, Clark Butler, and Lucas Bakers. Kalin and Sadivskova showed that the Holder continuity and the fiber branching assumption implied the convergence of canonical stable and unstable holonomy. That means for any y belonging to the local stable and unstable, a stable holonomy from x to y is equal to limit inverse a n y times a n x when n goes to infinity, and unstable manifold from x to y is equal to limit inverse a n y times a n x when n goes to minus infinity. This result was first proven by Bonatti, Gomez-Mont, and Vienna. And let me talk about an important definition in this talk. Bonatti-Vienna extended Furstenberg result to derivative cocycle. More precisely, the linear cocycle F satisfies the pinching and twisting condition if there exists a periodic point such that all eigenvalues of the AQ have a distinct value. There exists a homoclinic point Z of the P such that loop holonomy twisted ion direction of the AQ, where loop holonomy is equal to composition stable and unstable holonomy. The twisting assumption is weaker than assumption where Bonatti-Vienna assumed. Indeed, they require for any AQ invariant subspace whose dimension up to a number less than equal. As you see, I remove this assumption. Moreover, they work it on SLD, and I am working on GLD. I remarked, difference in the setting does not cause any problem in translating relevant statement and result from Bonatti-Vienna to this talk. And let me explain twisting assumption a bit more because maybe it's not clear for some of you. Look at this picture. This picture in the dimension 2, P is a periodic point, Z is a homoclinic point. Take any vector in the fiber projective like V1. We go to fiber projective at the point Z by unstable holonomy, and we come back to fiber projective at the point B by a stable holonomy. And the loop holonomy doesn't intersect any vector here. W is a set of the Holder and the fiber branching cocycle such that is a pinching and the twisting, and that's the open and the dense. And when I say a linear cocycle is a generic, it means its generator belongs to omega. I mean, it belongs to W, sorry. From now, level set means set of the point, the top Lyapunov exponent is equal to alpha. Lyapunov spectrum means set of the alpha such that there exists a point, a top Lyapunov exponent is equal to alpha, and omega is a set of the Lyapunov exponent measure. But natural question is as follows: what's the relation between the level set and Lyapunov spectrum? I will give you the answer soon. Lyapunov spectrum is a closed and convex. For locally constant cocycle, under irreducibility assumption was proven by Feng. For generic cocycle was proven by Park. For fiber bunching cocycle, I prove. Let A belongs to W, then Lyapunov spectrum is equal to closure set where the topology, where the entropy spectrum is a positive. Furthermore, entropy spectrum is a concave. Look at the following picture. As you see, entropy spectrum is positive in interior of the Lyapunov spectrum, and we don't know entropy spectrum at the boundary of the Lyapunov spectrum. I mean, we don't know entropy spectrum for maximal Lyapunov exponent. On the other hand, there is a conjecture that says entropy spectrum of the maximal Lyapunov exponent is 0 under generic assumption. Let me talk about this conjecture. For typical chaotic system xt and typical smooth function f, the maximizing measure is a unique and has a low complexity. In our context, low complexity means either 0 topological entropy or supported on a periodic orbit. This conjecture was proven for additive potential by Gonzalez Contreras, or precisely, if xt is an expanding map, then a generic Lipschitz function f from x to real number has a unique maximizing measure, which is supported on periodic point, more where the 0 temperature limit exists. Now we have the following open question. Is the conjecture true for Lyapunov exponent? That means we replace Birkhoff sum by matrix product. This conjecture is still open. I prove that the restricted variational principle holds for generic cocycle. More precisely, assume that the T is a topological mixing subshift finite type. Suppose that A belongs to generic cocycle, then topological entropy of level set is equal to supremum of the measured theoretical entropy such that mu belongs to a space of the T invariant Borel probability measure such that Lyapunov exponent measure is equal to alpha, and that's equal to infimum of the topological pressure minus alpha q, and the q belongs to real number, for all alpha belongs of the state of Lyapunov exponent measure. Let me explain this theorem in the following picture. The red is a graph of the topological pressure, and the blue line is a tangent to topological pressure at the point Q' with a slope alpha, and this intersection point is a topological entropy of level set, and that's equal to entropy for equilibrium measure mu Q', and that's equal to topological pressure minus alpha Q'. Let me talk about zero temperature limits for subadditive potential. Let phi be a subadditive potential for any mu belongs to a space of the T invariant Borel property measure such that log phi1 is integrable. Lyapunov exponent measure is equal to limit n goes to infinity 1 over n integral log phi and x d mu x. The maximal Lyapunov exponent that's equal to limit 1 over n log supremum of the phi and x over x, and that's equal to supremum of the Lyapunov exponent measure over the space of the T invariant Borel property measure. And the supremum attained, and I denote by m max phi the set of the maximizing measure. I mean, set of the measure that the maximal Lyapunov exponent is equal to Lyapunov exponent measure. And I prove that the zero temperature limit for subadditive potential, more precisely, let xt be a topological dynamical system such that the entropy map is oppressive continuous and topological entropy is finite. Suppose that phi is a subadditive potential on the compact metric space X, then any weak store accumulation mu of a family of equilibrium measure mu t for potential T phi where T positive has a Lyapunov maximizing measure. Let me remark that I'm just working with the accumulation. I'm not saying anything about the existence of the zero temperature limit. In fact, that's another open question. I mean, existence of the limit. And equilibrium measure here is not necessarily unique. I also prove that the continuous of the zero temperature limit in the sense of Lyapunov exponent and entropy. Limit of the Lyapunov exponent mu t, when t goes to infinity, that's the equal of the Lyapunov exponent maximizing measure, and we have the same story for entropy. Let us see when this theorem is true for Gibbs measure. We denote by Ln the set of the admissible word of the sigma with the length n. We denote by phi a the subadditive potential of the log norm an. We say that the mu t has the following Gibbs property for T phi, where T positive, there exists of this C greater equal 1 such that for any n belong natural numbers and cylinder G, we have a C minus 1 smaller equal measure of the cylinder over E minus topological pressure norm A and X smaller equal C for any X belong to the cylinder G. Let A belongs to W, then the previous theorem holds for Gibbs measure. In fact, we have a unique equilibrium measure which has a Gibbs properties. I also proved that the continuity of the entropy spectrum, suppose that AL and A belongs to W, with AL goes to A, and TL and T belongs to the positive real numbers such that TL goes to T. Let alpha TL be derivative of the topological pressure at the point TL, and alpha T be derivative of the topological pressure at point T. Then entropy spectrum of the EAL alpha L is equal entropy spectrum of the EA alpha. Moreover, entropy spectrum of the E alpha T goes to entropy spectrum maximal Lyapunov exponent when T goes to infinity. In other words, we have a continuity of the entropy spectrum at the boundary of the Lyapunov spectrum. Let X be a topological dynamical system such that the entropy map is upper semi-continuous and topological entropy is finite. Suppose that A from X to invertible matrix is a matrix cocycle over topological dynamical system, and Cx is an invariant cone field on X, then minimal Lyapunov exponent can be approximated by Lyapunov exponent of the equilibrium measure for the almost additive potential T phi A, where T belongs to real number. Moreover, a minimizing measure for A exists. And I prove that the continuity of the minimal Lyapunov exponent for derivative cocycle, or precisely, let T be a topological mixing subshift finite type. Suppose that A and A from X to invertible matrices are matrix cocycle over XT, and phi A has a bounded distortion. Assume that the CX is an invariant cone field on X, then we have a continuity of the minimal Lyapunov exponent. As I mentioned, continuity of the minimal Lyapunov exponent was proven for locally constant cocycle under one domination by Jairobocki and Ian Morris, and I proved that the continuity of the Lyapunov exponent for derivative cocycle under existent a cone field. In fact, those assumptions are equivalent. First, let me explain what I mean by domination. We say that A is I dominated if there exists a constant C greater 1 and tau between 0 and 1, such that the sigma is a singular value. Sigma I plus 1 A n x over sigma I n is smaller equal C tau n for all n and x. And Corvaisier and Potrier, they show that there is an equivalency between existence and cone field and domination. In fact, they extended Bocchi-Gormelan's result, who proved that for locally constant cocycle. Assume that F belongs of the diffeomorphism R greater equal 1. Let K be an invariant compact set, and the fixed D plus 1 greater equal 1. Then K is endowed with the DF, a contracted cone field C with domination, with dimension D plus, if and only if there exists a dominated splitting TKM with D plus is a dimension of the F. So by using of this theorem, we have the following theorem. Let AK and A belong to fiber bunching cocycle, and this, Euler continues and the fiber bunching cocycles implies bounded distortion. Assume that AK and A satisfy one domination, then we have a continuity of the Lyapunov, minimal Lyapunov exponent when AN goes to A. I think that's a good point to stop. Thank you for your attention.